All right, let's do some quantitative analysis, some additional examples. First, we'll do a few titrations. These are also going to be helpful for Lab 6. One of the things that we are doing is this actual titration using solid potassium hydrogen phthalate, which is sometimes abbreviated KHP. That's not the formula. It's not potassium and hydrogen and a phosphorus. It's potassium hydrogen phthalate. And this is the whole chemical formula. And so the molar mass of this potassium hydrogen phthalate is 204.22 grams per mole. So what we are trying to figure out in this problem is the molarity of our sodium hydroxide solution. So we need the moles of sodium hydroxide over the liters of solution. So the volume of solution we are told is 26.82 milliliters of our sodium hydroxide solution, and so that is just a metric conversion to get to liters. All right, so the other thing that we need to find out is the moles of sodium hydroxide, and I realized that I needed to have an equation down here to show you that it's a 1-to-1 ratio of sodium hydroxide to potassium hydrogen phthalate. So if we have the moles of KHP, we can get the moles of sodium hydroxide from that. And to get the moles of KHP, we can use the grams of KHP that we were told. So starting with our 0.458 grams of potassium hydrogen phthalate, we can use the molar mass. That gets us to moles of KHP. Then we can use the 1-to-1 molar ratio to get to moles of sodium hydroxide. And so that gives us 0.00224 moles of sodium hydroxide. I can keep a couple extra digits while I do this last step. And that step is to divide the moles, the 0.00224 moles, by the liters, which is 0.02682 liters of solution. And that comes out to be 0.0836 moles per liter sodium hydroxide. And I went down to 3 significant digits in this final answer. Another thing that we are doing in Lab 6 is this sort of analysis. We are using some sodium hydroxide solution now with a known concentration to analyze a monoprotic acid. And the reason why we specify that it's a monoprotic acid is that a monoprotic acid has a 1-to-1 ratio of reacting with sodium hydroxide. So we know that even though we don't know what this is, we know that it reacts with sodium hydroxide in a 1-to-1 ratio. So this is a little bit unusual because we want to know the molar mass of the acid. So we want to know how many grams per mole this mystery acid compound is. So to get the grams per mole, we know the grams. We're doing an analysis of 0.515 grams of our mystery acid. And then the moles of the acid, we can get that from the moles of the sodium hydroxide because our reaction tells us that we have a 1-to-1 molar ratio. And the moles of sodium hydroxide we can get from the volume of the sodium hydroxide solution, because we have sodium hydroxide solution with a known concentration. So we can get you can use the molarity to get the moles from the volume. So let's go ahead and start with our known 15.67 milliliter volume of sodium hydroxide solution. Convert that to liters, and then use the known concentration, and that concentration will get us from liters to moles. And then there's a 1-to-1 ratio with our monoprotic acid, so we can get moles of the monoprotic acid from that. And this comes out to be 0.003297 moles of our acid. So now we can put that in the denominator. I'm not sure why my screen disappeared, but I tried to recreate it so I could finish up this problem. We had just calculated that we have 0.003297 moles of our acid. We already knew that we have 0.515 grams of the acid. So to get the molar mass, we divide the grams by the moles. 0.515 grams divided by 0.003297 moles, and we get a molar mass of 156 grams per mole for our unknown acid. Okay, so I have a couple of gravimetric analysis problems using the same reaction. So this reaction is one that analyzes copper ions. You react with hydroxide to get copper 2 hydroxide. This precipitates out. It's a solid, but it's a little bit hard to isolate and work with, so you can heat it and get copper 2 oxide instead, and that is a little bit easier to isolate. So we do this in lab 7. So these problems should be helpful for that lab. All right, so we're doing the same kind of gravimetric analysis reaction on a solution and then also on a solid. For the solution, to calculate the molarity, we need to have the moles of copper over the liters of solution. The liters of solution we already know because we have 15.00 milliliters of it. So we have 0.01500 liters of solution. The moles of copper we're going to get by starting with the mass of copper 2 oxide that precipitated. Then we can go ahead and convert it to moles with the molar masses that I just added up there in the corner. And then once we have moles of copper 2 oxide, it is a 1-to-1 ratio between copper 2 oxide and copper ions. Then we divide that 0.00357 moles by the 0.01500 liters, and we can figure out that our original solution was 0.238 molar in copper 2 ions. All right, so this next one we want to get the mass percent of copper. And in order to get the mass percent of copper, we need to know the mass of copper, the total mass of our compound, and multiply that by 100%. So we know the total mass of our compound. We had a sample that was 1.855 grams total. Now we just need to know how many grams of copper are in there. And we'll have to use the copper 2 oxide to figure that out. All right, our 0.842 grams of copper 2 oxide can be converted to moles using the molar mass. Then there is a 1-to-1 ratio of 1 mole of copper 2 oxide for every mole of copper 2 ions. If you want to add in an extra step saying that there's 1 copper atom for every copper 2 ion that is in the solid, that's okay. Or we can just use this molar mass. The molar mass of a copper 2 ion is essentially the same as the molar mass of a copper atom. The 2 missing electrons do not affect the mass very much at all. And I'm getting 0.673 or 0.67265 grams of copper 2 ions. So our grams of copper or grams of copper ions in the solid was 0.672. You can use a couple extra digits. That's how much of the mass was copper. 1.855 grams was the total mass. And so that comes out to be 36.3 mass percent copper in the sample. And we're limited to 3 significant digits just because the mass of copper 2 oxide only had 3. All right, let's do a couple of examples on combustion analysis. I'm going to do one that only has carbon and hydrogen, and then also try one that has carbon, hydrogen, and some oxygen in it. So what's happening is you are burning a sample in oxygen and getting carbon dioxide and water as the products. So any carbon that is in your sample is going to end up as carbon dioxide, and any hydrogen that's in your sample is going to end up as water. So the empirical formula, if you recall, is the simplest molar ratio of elements. So to figure out this molar ratio, we are going to need the moles of carbon and the moles of hydrogen, and then if these come out to be strange numbers, we're going to try to use some of those tricks to get them to be whole numbers or integers for our molar ratio. So we're going to get the moles of carbon from the carbon dioxide. We obtained 0.1888 grams of carbon dioxide from this combustion analysis. All right, I got some molar masses up there now, so let's go ahead and use that. That will convert to moles of carbon dioxide. And each mole of carbon dioxide was made using 1 mole of carbon. There's 1 mole of carbon in every 1 mole of carbon dioxide. So that can give us some moles of carbon. And that gives us 0.004290 moles of carbon in our sample. So any hydrogen that was in our sample ended up as water. We can convert the grams of water that we isolated into moles of water. Then with water, we need to remember that there are 2 moles of hydrogen in every 1 mole of water that was created. And so that ends up with 0.0100 mole of hydrogen. I'll just keep a couple extra digits here. So this is the molar ratio, but we do want to try to get some whole numbers so we can make a formula out of it. So we're going to divide both by the smaller number. When we divide the carbon by the smallest number, we end up with 1 mole of carbon. When we divide the hydrogen by that same number, we end up with 2 1/3 moles of hydrogen. Alright, so we don't have whole numbers at this point. Sometimes you do, but this time we have 2 1/3. So to get these to be whole numbers, we are going to have to triple them. When we triple the 1 mole of carbon, we end up with 3. When we triple the 2 1/3 moles of hydrogen, we end up with 7. So our empirical formula now can be written with this simplest whole number ratio of carbon to hydrogen. It's C3H7. Let's try a slightly more complex example because we have carbon, hydrogen, and oxygen. So remember, we can figure out our carbon from how much carbon dioxide we get, and we can figure out our hydrogen from how much water we get. The oxygen, we have extra oxygen around, so these oxygens in the carbon dioxide and the water could have come from the sample, or they could have come from the extra oxygen. So what we're going to have to do is figure out from the mass of our sample what mass of carbon we have and what mass of hydrogen we have in there, and then get the oxygen by subtraction. So first let's figure out our moles of carbon and moles of hydrogen like we did on the previous example, because the molar ratio needs the moles of carbon, the moles of hydrogen, and the moles of oxygen. So let's go ahead and use the carbon dioxide to calculate the moles of carbon. So we have the molar mass, and this comes out to be 0.0190 moles of carbon. Let's write that down over here. And then we can use the water to get the moles of hydrogen. So we convert the 0.342 grams of water into moles of water. And that ends up, when we take the 0.342 grams of water, convert that to moles, and then remember there are 2 moles of hydrogen for every mole of water, we get 0.0379 moles of hydrogen. Actually, these are large, so it could bump up to 0.380. Now that we know both of these amounts of moles, we can figure out how many grams that is. So we'll take these moles, convert the carbon to grams using carbon's molar mass, convert hydrogen using hydrogen's molar mass. So 0.037966 moles of hydrogen would be 0.0383 grams of hydrogen. 0.0190 moles of carbon would be 0.2284 grams of carbon, only with 3 significant digits. So if we take the total amount of sample that we analyze, 0.368 grams, and we subtract the amount of carbon and the amount of hydrogen that are in there that we just figured out, then we are left with 0.102 grams of oxygen in our sample. The 0.102 grams of oxygen represents 0.00638 moles of oxygen in our compound. So now we have a molar ratio of carbon to hydrogen to oxygen in our compound. But we need to get these to be more normal looking whole numbers first before we can try to make a formula out of it. Alright, oxygen's is the smallest number, so we'll go ahead and divide by that number. And then when we divide this by the smallest number, we get 6 moles of hydrogen. It's 5.95, so it's pretty close to 6. When we divide the moles of carbon by this small number, 0.00638, we get 3 moles of carbon. So we get all 3 of these being whole numbers right away. And so the empirical formula of our compound here would be C3H6O.